Hello. Today we're going to be having a look at combinations and permutations and different ways of arranging different objects. Now, if you remember back to when Mr. Crofts came into the class to film some footage for the sixth form promotional video, you remember dropping lots of coins, and this is linked to some of the work on Pascal's triangle that we did back then. But we're going to go through it again just to make sure that you know the basics and can answer some of the questions from the exercise in the textbook, which I will tell you the page number for in a moment. This stuff is on page 186 and 187, so that's exercise 2.1 and exercise 2.2 that we're looking at the start of this week. So, arrangements, I've got 3 coins here. There's 1 brass, 1 copper and 1 silver, and I'm just going to look at different ways I can arrange these different coins. So I could have my brass first and then copper, silver. If I'm sticking systematically, I could keep the brass there and I could swap the copper and the silver around. So then I've got brass, silver, copper. So I'm going to write those 2 down. I've got brass, copper, silver. I could also have brass, silver, copper. I could also do it so that the brass isn't at the start, so let's put the silver at the start instead. So I could have silver, brass, copper. I could swap those 2 around and have silver, copper, brass, and I can do it one more way, so I could have the copper at the start. So then I've got copper, silver, brass. Swap those 2 around. I could have copper, brass, silver. Notice I've done this systematically. Brass is at the start, silver's at the start, copper's at the start, and I've laid it out in a way such that I can look at this and say I've done all of the different combinations that there are. Now you notice that for 3 here there are 6. There's a way of working this out without needing to actually have some physical medium to move around, and that way is to use factorials. So a way of thinking about this is, well, if I've got no coins here and I want to put something in the first position, if I've got choice of these 3 coins, how many coins are there to choose from to put into the first position? Well, there are 3 coins. So let's just chuck one of them there just as an example. Next position, how many coins have I got left to put in the second position? I've only got 2 coins left here, so I'm going to put that one there just as an example. So 2 coins left. And then finally, in the last position, there's only 1 coin left to choose from, so I've only got 1 coin. So 3 times 2 times 1 is 6. Now this here is what's called a factorial. We use an exclamation mark to denote a factorial. So 6 factorial, apologies, 3 factorial here is 3 times 2 times 1, which gives us 6. If I had 4 items and I wanted to know how I rearrange 4 items, it would be 4 factorial, which is 4 times 3 times 2 times 1. So if you're asked how many different ways there are of arranging things, it's the number of items that you've got with the exclamation mark, which is factorial. You can find this on your calculator if you have got particularly large numbers that you don't want to work out yourself, and that's here on the Casios, so it's just above the x to the -1 button, below the mode button here. So you've got to use the shift function to get access to it, but as you can see here at the top of the calculator there, I can do 3 and then shift, push this button here, 3 factorial equals, and that gives us an answer of 6. So that works out 3 times 2 times 1 for us. So what other things can we do with these? We've already seen these kind of arrangements before. I want to have a look at some of the other things that we can do. So one of the other things that we can do are these things called combinations. So if I have these 3 coins, I want to know how many different ways there are of picking a certain number of them. So let's say here I want to choose 2 coins from 3. So I've got 3 coins, I want to choose 2 of them. So I could choose, say, copper and brass. So that's copper and brass. I could choose brass and silver, or I could choose copper and silver. Now, I know what you're thinking. You think, oh well, could I choose silver and copper? Well, it's the same pair of coins, isn't it? It doesn't matter whether they're that way around or that way around. Copper and silver, silver and copper, it makes no difference. The point being here is I would just want to simply pick 2 coins from those three. Now these are what are called combinations, and there's a way of working out how many different distinct ways there are of choosing 2 coins from 3. Here we found that there are 3, and you can do it using the following calculation. On the calculator it's this C button, so you'd write 3 C2, 3 items, and I'm choosing 2, or 3, C stands for combination, but we read it as 3 choose 2, and the calculation to work this out is 3 factorial, so that's this number here, divided by 2 factorial, that's this number here, and then 1 factorial, so this here is the leftover bit to make it up to 3, so 2 add 1 here would add up to 3. I'll show you another example of how we can work this out in a second, and that would give us 6 divided by 2, because this is 2 times 1, times by 1, so this is 6 divided by 2 times by 1, which gives us 3, which is this the number of different combinations we've got here. Now, as I say, we can work this out on the calculator. I'll show you how to do that now. So on the calculator, the combinations button is here. Let's move that up. Here, just above the divide sign. Again, you've got to use the shift symbol to be able to get access to it. I'll just turn the light on there. That's maybe a little bit better. So you've got to use the shift button to get access to that there. So I'm going to do here shift, 3 shift divide, so that gives us a C on the screen, 2. So 3 choose 2 push equals, as you can see there it gives us an answer of 3, which we've already worked out using our formula. Now I'm going to write down what the general formula is for this, just so that you've got it and you can write it down should you wish to know it. So if I've got some number n and I'm choosing r items from that list of n, then it's going to be n factorial over r factorial, and then it'll be n minus r factorial. So let's do an example of that. Let's say I was doing, I don't know, 7 choose 5. It'll be 7 factorial on the top divided by 5 factorial and then 2 factorial, because 5 add 2 gives me that 7 on the top, in the same way that 2 add 1 there gave me that 3 on the top. Now again, you can work all of these individual numbers out, cancel things off and stuff like that. However, all of your exams are calculator exams, so long as you know how to access that C button there that is just above the divide sign on the standard scientific calculator, then you should be fine. You don't need to be able to work these things out by hand. One other thing that you should be mindful of is where else these appear. So these here appear in Pascal's triangle. They also appear in binomial expansions, which we have looked at. So you'll recognise this notation here from binomial expansions. It's exactly the same, it's just used in a different place in here. We're looking at choosing things from different items from a list. Say, for example, here we've got 3 coins and we want to choose 2. Permutations, however, are slightly different, so we haven't come across permutations. They're a similar sort of idea, except here we said that the order didn't matter, whereas with permutations we are going to consider that the order does matter. So if you're asked to work out something where, for example, you might have say first and second, so they're winning the race or coming second in the race are 2 distinctly different things. So if we again look at this idea of choosing 2 from a list of 3, so again if we're looking back at these 3 here, we could have copper and brass, so that's these 2, but you could also have it the other way around. You could have brass and copper. Now if we're thinking in terms of permutations where the order is important, so it could be coming first in a race, coming second, Charlie comes first and Bob comes second, compared with Bob comes first and Charlie comes second, then here having it the other way around makes a difference. If you're just thinking in terms of choosing 2 coins from a list of 3, then yes, it's a combination that you're looking for, and the order doesn't matter. But here, if you're looking for, say, positions in a race, then the order does matter. We also had brass and silver, so we could have silver and brass, and then finally we had copper and silver, so we could have silver and copper. Again, this is something that you find on the calculator. So the C button here was above the divide. If you just look a little bit to the left of that, above the multiply sign, there is the P button there. That's for permutations. So if I do 3p2, so let's do 3 shift, multiply, gives me the p up here, and 2, so 3p2 equals, there we go, we get 6, which is what we should expect because we had 6 things on our list if the order made them distinctly different things. Now, for these two small lists, there's not much difference here. You've got 6 versus 3, and you think, oh, well, is it always double? Well, it's not. Let's choose one. Let's say we did 9, choose 6. So I want to choose 6 items from a list of 9. How many different ways are there of choosing 6 items from a list of 9? I push equals. There are 84. I can move that so you can actually see it, so it's not in the light. 84 different ways here of choosing 6 items from a list of 9, so that's quite a lot. If I do 9p6, so again I'm looking to choose 6 items, but the order is important. There's 60,480, so that's a heck of a lot more than the 84 different ways of picking where order didn't matter. So you need to make sure you know the difference between these two, and you look at the question to make sure that you understand, does it matter whether there is order here or not? Is it first and second, etc., like races and stuff? Then permutations are what you're looking at. If, however, it's just simply choosing items and the order doesn't matter, it's combinations that we're looking at. So we're going to have a look at a couple of questions and look at using some of these calculations. So I'm going to put my calculator off screen, but I'll be using the same functions and writing some of the stuff down for these questions. So these are the typical kind of questions that you might get. So here, the first one, there are 30 students in a class. A team of 4 students is chosen for a math challenge. How many ways are there of choosing a team of 4? So this one here, it doesn't matter what order they're picked in. So I just want to choose 4 students from the class of 30. So here I want to do 30, I want to be choosing 4. So 30 choose 4, we can do that on our calculator. So here I can do 30, choose 4, there are 27,405 different ways. So 27,405 different ways of picking 4 students from a class of 30. That's a lot. Next question. So there's 10 boys and 10 girls in a tutor group. A committee of 2 boys and 2 girls is to be chosen. How many different ways can the committee be chosen? So here you've got 2 distinct groups. The temptation here would be to add these together and say, well, I've got 24 and I want to choose 4, and then do 24 choose 4. However, if you have 24 choose 4, then that includes things that we don't actually want to include, so you'll get a greater number there. So if we just work out what 24 choose 4 is, so we do 24 choose 4, we get 10,626. Now our answer is not going to be as large as that, because 24 choose 4, so if I do the total here and then do the total here, that includes things that I'm not interested in. For example, it includes the prospect of having, say, 4 boys or 4 girls. Well, I'm not interested in either of those. I'm not even interested in having, say, 3 girls and 1 boy. I want 2 boys and I want 2 girls. I want all the different ways I could choose those. So what we do is we work out how many different ways there are of choosing the boys, how many different ways there are of choosing the girls separately, and we multiply those two numbers together. So here we're going to do 10 choose 2. I'm going to multiply that by 12 choose 2. So here on my calculator, I'll just put that out shot so that you can see. So 10 choose 2, so that gives me 45, multiplied by 12 choose 2 was 66. So 45 multiplied by 66 is 2,970, which is much smaller than if we did 24 choose 4. So you've got to be careful with questions like this where they've maybe got 2 groups and you want to use those 2 groups or even more than 2 groups in order to generate one final group. You've got to remember to do it separately. So here we did the boys and the girls separately, and then we multiplied their individual amounts together. So as a reminder, you are looking at page 186 and 187, so there's 2 exercises there, exercise 2.1 and exercise 2.2. I'll do another video this week and we'll be then looking at how we can use this in the binomial distribution in much the same way that we use this in binomial expansions. Combinations here are going to be very useful for that, and we're also going to merge that with what we were looking at last week, which was simple probability distribution functions. So we're going to have a look at a very specific and very useful probability distribution function, which is the binomial distribution, and we're going to do an extensive chunk of work on the binomial distribution.